Hello everyone, so in this video we will be discussing length of a curve. So we have here the equations of the length of a curve. So basically, as you can observe, they are just similar. However, this first equation is used when you are finding the integration or the length of a curve with respect to x. And the second one is when you are looking for the length of a curve with respect to y and with respect to theta or the angle. So we have here the integral of square root of 1 plus the derivative of our function squared and with respect to x. And we have the limits from a to b. So we have here the example, find the length of the curve y is equal to ln of secant x from x is equal to 0 to x is equal to pi over 3. So in this case, as you can see, our function is equivalent to y, meaning to say we will be using the first equation, which is finding the integral with respect to x. So the first thing that we need to do here is to find the derivative of our function, which is ln of secant x. So doing that, we have y. Again, y is equal to ln of secant x, in which we know that in order for us to find the dy over dx, the derivative of our ln secant x is the denominator is the u, which is the secant x. In the numerator is the derivative of our secant x, in which, as we know from differential calculus, the derivative of secant x is equivalent to tan or tangent x secant x. And we can cancel the secant x, so meaning to say our dy over dx is equivalent to tan x. So from that, we can already use the equation s is equal to a to b square root of 1 plus squared of dy over dx, or the derivative of our function, square root, and we have the dx. As we know, dy over dx is equivalent to tan x, so we'll just plug that into our equation. So we have our limits, the upper limit and the lower limit is this one, as you can see. X is equal to 0 is our lower limit, and pi over 3 is our upper limit. Now, substituting again our derivative of the function, so we have tan x, then squared, then we have the dx. Afterwards, we have to simplify our function. So we have 1 plus tan squared x, in which we know this has an equivalent trigonometric identities. As we all know, 1 plus tan squared x is also equivalent to secant squared x. So meaning to say, 0 from 0 to pi over 3, 1 plus tan squared x can also be written as secant squared x. And then to find the square root of this one, we can just cancel the squared and the square root. So meaning to say, what we have left is 0 to pi over 3 and then the secant x dx. So as you can see, it will be easier now to integrate this kind of function. As we know, the integral of secant is equivalent to ln of secant x plus tan x. And then we have our limits from 0 to pi over 3. Now substituting our upper limits and the lower limits to our resulting function, so we have ln of secant pi over 3 plus tangent of pi over 3 minus ln of secant of 0 plus tangent of 0. And if you calculate this one, this part is also equivalent to 0, so meaning to say you can just cancel that one. And if you calculate this one, this is approximately equal to 1.317 units. So this is now the resulting length of our curve. So we have here another example. Determine the length of x is equal to 2/3 y minus 1 raised to 3 halves between y is equal to 1 and y is equal to 4. So in this case, as you can see, our given function is equivalent to x, meaning to say we will be using the second equation. We will be finding the integration or the length of the curve of this problem with respect to our y. So in this case, we need to find the derivative of our x, which is dx over dy is equivalent to 2/3 times the exponent of our function, which is 3 halves. Then we have y minus 1 raised to 1/2. And as we know, if you multiply this one, this is equivalent to 1. So meaning to say, the derivative of our function is equivalent to square root of y minus 1 or y minus 1 raised to 1/2. So we can already plug that one to our equation, which is s is equivalent to 1 to 4. This is our limit, which is stated here. And then we have square root of 1 plus square root of y minus 1 squared. Then we have our dy. So afterwards, we know that the squared of a square root is also equivalent to 1. So meaning to say, we can just rewrite this one as equivalent to 1 plus y minus 1, since we already canceled the square root and the squared. Then afterwards, as you can see, 1 minus 1, that is equivalent to 0, so you can cancel that one. So meaning to say that the integrand left is y, square root of y or y raised to 1/2 dy. And we all know that we can apply power formula for this one. So basically we have y raised to 3 halves all over 3 halves, and then we have our limits from 1 to 4. So substituting our upper and lower limits to our resulting equation, so we have 4 raised to 3 halves all over 3 halves minus 1 raised to 3 halves over 3 halves. Now, as we all know, if we calculate this one, this is equivalent to 14 over 3 units. So meaning to say, this is now the final result of the length of a curve. So we have here another example. Find the length of one branch of the curve 9y squared is equivalent to 4x cubed from x is equal to 0 and x is equal to 3. So in solving this kind of problem, if you want to sketch a graph of this function, 9y squared is equal to 4x cubed, you need to substitute again some values to our x and our y. So in this case, if we substitute some values to our x and y, And we know that the limits of our x is from 0 to 3 only. So meaning to say, if you substitute 0 to our value of x from this function, we have y is also equal to 0. And if you substitute 1 to our x, the value of our y is equivalent to 2/3 or approximately equal to 0.7. And if you substitute 2 to the value of our x, so we have 4 square root of 2 over 3, which is approximately equivalent to 1.9. And finally, if you substitute the value of x by 3, this is equivalent in y by 2 square root of 3, which is approximately equivalent to 3.5. Now, if you try to sketch or if you try to plot this one to our Cartesian plane, we have our 1, 2, and 3. We have 1, 2, 3, and 4. So 0, 0, that is somewhere here at the origin. We have 1 and 0.7, so it's around here. 2 and 1.9, it's almost 2. 3 and 3.5, it's around here. But it says here that one branch of the curve, so meaning to say, if we continue graphing this one into its opposite sign, so meaning to say if you plot -1 here, that will result to -0.7 and so on and so forth. It's basically the same with the given result but in negative sign. So if we also try to plot this one below, we have 1, 2, 3, and 4. Plotting that one, we have 0.7, we have 1.9, and we also have -3.5. And we know that our curve is bounded by x is equal to 0, which is this one, and it is bounded by x is equal to 3, which is this line. So meaning to say that is already enclosed. Our curve is already enclosed. Supposing we already connected the points, you just have to suppose that one. I'm no good in this graph. So meaning to say we are to find the distance covered with this curve, or what is the length of this curve. Now, continuing to our solution or to our problem solving, we know that we can use either x or y from here, but since the given limit is x, so we'll just use the first equation. So using the first equation, we have to isolate our value of y here. So from 9y squared is equivalent to 4x cubed. We need to isolate y again. So meaning to say we need to divide both sides by 9. So we have y squared left. So y squared is equivalent to 4x cubed all over y. And then to isolate y or y squared, we can square root this and this one as well. So basically y is equivalent to square root of 4x cubed over 9. So this is now our function that we will be using afterwards. After we find the equation that we will be using, we all know that we need to derive this one, or we need to derive our function. So dy over dx is equivalent to, this is also raised to 1/2, right? So we have 1/2 times our function 4x cubed over 9 raised to negative 1/2 multiplied by the inner one. We have 4 over 9 times 3, then we have the x squared. Now simplifying this, we have 2x squared all over 3 square root of 4x cubed over 9. So basically this is what we will be using for the integration of our length of the curve. So we have s is equivalent to 0 to 3, since from these limits we have 0 to 3. And then we have the square root of 1 plus our dy over dx squared, which is this one. So we have 2x squared all over 3, and then we have the square root of 4x cubed over 9, and then we have the squared and the dx. So afterwards, we need to simplify first what's inside our radical sign. So we have integral of 0 to 3 square root of 1 plus, as we know, if you raise this a fraction to a squared, you can just separate that one but still in squared. So we have 4x to the 4th over 9, and for this one we have 4x cubed over 9. We have the dx. So basically we can just simplify this again. So we have plus, we can cancel this one, and then we can cancel this one. So maybe say this is raised to 4 and this is raised to 3, so we still have 1x left. Then we have the dx. So we can just simply transform this one to exponential form. So we have 1 plus x raised to 1/2 dx. Now, as we all know, we can already use a power formula for this one. So the integral of our integrand is 1 plus x raised to 3/2 all over 3/2. That is from 0 to 3. So substituting again the limits, our upper limits and the lower limits. So we have 4 raised to 3/2 all over 3/2 minus 1 raised to 3/2 all over 3/2. This is equivalent to 14 over 3 units, meaning to say this is now the length of our curve. So thank you so much for watching the video, and I hope you don't forget to like this video, and I'll see you on the next one.